This is an example of a circuit containing a voltage-controlled current source and useful to model a circuit with a polar junction transistors. In the second half of the semester, we are going to study bipolar junction transistors. A bipolar junction transistor is a three-terminal device that when it's powered up with a DC source and we apply a small signal, it can be used for amplification. A bipolar junction transistor has three terminals. The base, which is labeled as B, the collector, which is labeled as C, and the emitter, which is labeled as E. Now, this model has a resistor connected between base and emitter that we call R pi, and has a dependent current source. This current source depends on a voltage. The voltage between base and emitter labeled as VBE. And then we have an output resistance connected between collector and emitter called RO. Okay, so what we have is a circuit that uses the bipolar junction transistor and has a signal, okay, that we are applying, which is Thevenin equivalent representation, has a Thevenin equivalent resistance and a voltage source is being applied to the input of the amplifier, in this case the voltage from base to emitter, okay? And now we are taking an output voltage in the resistor connected between the collector and the emitter. Now in this exercise, we want to derive an expression that relates the output voltage to the input signal voltage. So we have two approaches. The first approach consists of going from the input to the output. Okay, so we can use the voltage divider rule to find the voltage between base and emitter. Simply multiply the input voltage times the second resistor divided by the sum of the resistors, and just remember that this is only applicable when the resistors are in series. In other words, they share the same current. Now we can find the output voltage using plain Ohm's law, voltage times and current times resistance to find the voltage. In this case, V out is going to be equal to the current, GMVBE, times the equivalent resistance. The equivalent resistance is the resistor RO in parallel with RL, and that's because the resistors are connected in parallel. In other words, they share the same voltage. Now, as you can see, the arrow is pointing away from the resistors. Therefore, we have to apply a negative sign just to make it dimensionally consistent. Last step, substitute the equation from step 1 into the equation from step 2, and just express our output voltage as the input voltage times the transconductance times the output resistance, and that gives us an expression for our output voltage. The same problem can be done with a second approach, which is from the output voltage to the input voltage. In other words, find first an expression for the output voltage and then relate that to our input voltage. So in this case, we can use Ohm's law again, multiply the current times the resistance. The current is GMVBE times the resistance, which is RO in parallel with RL, and with a negative sign as the direction of the arrow is away from the positive sign. Now we can use the voltage divider rule to find the VBE, which is what we are missing from our first equation. In this case, it's just Vs times R pi divided by the sum of the resistors, as the Rs is in series with R pi. Then finally, we substitute our second equation in the first one, and we have then a total expression for the voltage gain of this circuit, just combining the two equations. To complete the exercise, let's just use a numerical substitution to see how the numbers play out and what the answer is numerically. In this particular case, we can just substitute the values that we have. The source resistance is 5 kilo ohms, R pi is 3 kilo ohms, transconductance 25, our output resistance is 80, and RL is 8 kilo ohms. So we just substitute in the equation from the previous step and find that V out over Vs is equal to minus. Notice that I'm substituting the resistors in kilo ohms, and if I do the transconductance in milliamps per volt, the units take care of each other. 3 divided by 3 plus 5 is basically non-dimensional, right? Then you have 25 milliamps per volt multiplied by 80 divided with 7 kilo ohms becomes a non-dimensional amount, and that gives us minus 60.34 volts. In other words, a voltage gain from output to input of 60.3, and is inverting. That means the gain is negative. And basically that's it for this program.